Okay, good morning. And I would like to thank the organizers for inviting me. And today I decided to discuss one aspect of antiferromagnetic high-frequency spin dynamics, which we realized only a few years ago. And I think it may have important implications for interpretation of experiments or even theoretical analysis. So I will give you two examples that strong coupling between magnons and electromagnetic waves forms the hybrid excitations called polaritons. So, and I will discuss two experiments. So the reason stop working. It's frozen for some reason. Yeah, thank you. Yeah, sorry for this. So the first experiment I did at Radboud University in the group of Professor Alexei Kimmel, and the main kind of person who helped me was PhD student Kirill Vishunin. And another experiment was done in collaboration with the group of Professor Rupert Huber in University of Regensburg. So as we already know, so there are two ways to excite spin dynamics in antiferromagnets. So kind of the first is the excitation by the femtosecond laser pulses, which was demonstrated in this important paper in 2005. So alternative approach is the direct excitation by the resonant Terahertz magnetic field. So it was first demonstrated later in 2011. So in all these experiments, so the kind of the first interpretation was to assume that it is the homogeneous excitation. So the antiferromagnetic mode has 0 k vector. But at the same time, we need to bear in mind so that if there is a resonance at Terahertz frequency, so the spins oscillate, so that creates the magnetization, which is a function of time. And magnetization, which is a function of time, is just a magnetic dipole. But magnetic dipole will emit electromagnetic radiation. And this power of the emission grows as a frequency squared. So it is expected to be more pronounced for Terahertz dynamics in antiferromagnets compared to lower frequencies in ferromagnetic materials. So I will argue that it is, in many experimental situations, it's more correct to talk not about Terahertz magnons, or but about polaritons. So we can simply see it on this diagram. So we have, so in the simplest case, ignoring all inherent dispersion of the magnon, at some point in the frequency wave vector map, it will cross the line describing the dispersion of light. And then the hybrid mode polariton will be formed. So there will be upper and lower branch in the case of the zero damping. So the question is whether we can see the signatures of these polaritons in the experiments. So the first experiment we've done was Terahertz time domain spectroscopy on antiferromagnet thulium orthoferrite. And here, what is important for us now is that one of the antiferromagnetic resonance modes has frequency of 0.8 terahertz. So here you can see a schematic of the experiment. So we have the femtosecond laser. So then we split the laser beam into the two branches. So the stronger beam illuminates the electro-optical crystal, which generates terahertz waves, which are then focused onto the sample, which sits inside the cryostat, for example. And we'll look at how these waves propagate through the sample. So the transmitted waves we can then focus onto another electro-optical crystal, which is simultaneously gated by this weak probe pulse. So the electric field of the terahertz wave induces optical axis in the electro-optical crystal, creating optical anisotropy. Thereby, the gating pulse requires electricity proportional to this electric field of the terahertz wave, and by changing the delay, we can record the time trace of the propagated terahertz radiation. So here you can see examples of terahertz transmission through thulium orthorite at different temperatures. So here are the signals in the time domain. On this panel, you can see the corresponding spectra. So this dip corresponds to the frequency of the antiferromagnetic mode. So that is kind of expected and not surprising. But if you look carefully into the time domain signals, there is a clear beating instead of expected just exponential pre-induction-like decay signals. So then we modified our experimental scheme to measure, instead of terahertz transmission, the terahertz emission. So that's we illuminate our sample directly by this strong 800 nanometer pulse. So then again, by means of impulsive stimulated Raman scattering, this pulse can excite the magnon of the material, and we can then measure emission instead of transmission of the terahertz wave. Again, here you can see the time domain signals together with their spectra. And as in the case of transmission, here again, instead of the quasi-monochromatic signal, there is a clear envelope on top and the beating in the time domain, while in the frequency domain, it corresponds to the splitting of the Magnon band. So how can we explain these observations? So let's start with the transmission geometry. So what we can do, we can solve Maxwell equation for the propagation of our experimental terahertz waveform, taking the known tabulated magnetic permeability function for this resonance mode. So after solving Maxwell equations, you can see that without any fitting parameters, we can reproduce very well the features observed in the experiment, so the beating in the time domain and the splitting of the magnon in the frequency domain. So we can also apply similar analysis to the emission geometry. So here, of course, we need to have a model for the laser-driven excitation. So we do it in a very simple way. So we assume that light acts as a pulse of effective magnetic field, which follows the envelope of the laser pulse. And then again, we solve equation of motion of spins together with the Maxwell equation in response to this excitation. And again, you can see that we can reproduce the main features of the experiment, so the phase sweep and the splitting of the mode in the frequency domain. So here the only fitting parameter was the effective magnetic field amplitude, which we obviously don't know. So it seems that just the simple analysis based on the Maxwell equation already allows us to explain this experimental observation. And this beating is nothing else as the beating between the polaritons in the upper and lower branches of the dispersion curve, which is formed near the crossing line between the Magnon frequency and the line light dispersion line. And this is an illustration that propagation effects, so the effects are connected to the electromagnetic component of the Terahertz Magnon excitation is important in the conventional Terahertz experimental geometries. So the second question I would like to discuss, whether it also may have any implications for the Terahertz-driven spin control. So for example, we have done experiments when we use the strong Terahertz pulses to excite our samples. And we looked at the material called dysprosium orthorite. So it's a similar antiferromagnet, which has two antiferromagnetic resonance modes. And importantly, there exists a temperature at which the frequencies of these modes become equal to each other. So in principle, it may be considered just as a kind of coincidence, because the modes are assumed to be normal to each other, so nothing special around this temperature point is expected. So nonetheless, we try to pump our sample near this temperature with a strong Terahertz pulse, and then we trace the magnetization dynamics by measuring Faraday rotation of the femtosecond optical pulse delayed with respect to the pump. So importantly, here, our sample was cut perpendicular to its optical axis, so which was supposed to remove any parasitic effects connected with the birefringence in this material. And here you can see the indicative waveform of our Terahertz pulse and corresponding spectrum. So again, on this graph, you can see the time domain Faraday signals, which essentially is a sum of two oscillations corresponding to the frequencies of two antiferromagnetic modes in this material. So we can then extract these frequencies experimentally and confirm that indeed there is a temperature where they cross each other. But if you look carefully at the time domain signals, you can clearly see that around the temperature, so say 150 Kelvin, corresponding to this point, the amplitude seems to be enhanced. It becomes even more apparent if we look into the spectral amplitudes of these modes. So on this chart, you see how the spectral peaks evolves with the temperature, and as you may notice, as the frequencies cross each other, the amplitude clearly is not just the sum of the amplitudes of the modes taken separately. So I can even integrate the spectral weight and plot it as a function of temperature. So here you can clearly see the peak. So the question is, what is the origin of this enhancement. So it can be understood with a very simple model of internal resonance. So imagine you have two harmonic oscillators, so corresponding to these two orthogonal modes. And then you can introduce some coupling between them. So I just do it for the simplest case. So you can imagine also other forms of the coupling can be here as well, or you can take time derivative instead of just antiferromagnetic vector component. So this will lead to the appearance of the additional term in the response in the frequency domain, which will peak when the frequencies of the modes will become equal. So for some indicative parameters, I can plot this integrated response. And again, so here you see this detuning between the frequencies, and there will be a peak in the solution. So this indicates that probably we have some coupling between the modes. And that's why when the frequencies become equal, there is an enhancement of the Terahertz-driven response. But the question is, what is the origin of the coupling? Because in principle, the model assumes when we derive these modes that they are orthogonal to each other, so they don't couple by definition. Okay, so one of the possibility is that our strong field is enough to drive the system into the nonlinear regime. And maybe in that case, the nonlinear coupling terms arise. However, we performed our experiments for very different Terahertz driving fields amplitudes. So here you see the normalized with respect to these amplitudes signals. And they are practically identical, meaning that there is no nonlinearity, at least for the fields used in the experiments. So this is nonlinearity is ruled out. So then we also have dysprosium sublattices. So maybe there is some coupling mediated by the Rayos subsystem. However, we performed the theoretical analysis based on symmetry, and in no way this can add to any additional coupling terms. So one may also think about kind of complexity of the ground state, some kind of domain distribution, but I think it's too complicated. And instead, I will argue again that this is propagation effects connected to this polaritonic nature of these modes, which leads to this coupling. So again, I already stressed a few times that in the model, the modes are assumed to be orthogonal. But again, this is derivation is based simply on the basis of the spin dynamics equations, which neglect the electromagnetic component. However, we already confirmed that in the orthoferrites, the modes are in fact polaritons, so they propagate. And these crystals are highly birefringent for the for light at Terahertz frequencies. The difference in the I think between the velocity of extraordinary and ordinary waves is even bigger than in quartz for optical waves. So this we can even take the dielectric permittivity tensor for the orthoferrite, and you can see that there is a huge difference actually between the permittivity components. At the same time, the variations in the magnetic permeability are much smaller. So that means that anisotropy is mainly coming from the dielectric properties. So based on this dielectric tensor at Terahertz frequencies, we can calculate the direction of the optical axis. And we note that the optical axis at Terahertz frequencies deviates from the direction of the optical axis for our 800 nanometer pulse by about 15 degrees. And you know that in the birefringent material, 15 degrees is already a very big factor. So I think I started 5 minutes later. So that means that when you propagate, so when our Terahertz pulse propagated along the sort of incorrect optical axis, that means that the magnetic field produced by the modes of the antiferromagnetic resonance were not anymore the eigenwaves in the birefringent system. Instead, you need to calculate the new basis based on these ordinary and extraordinary waves, and then obviously these modes won't be orthogonal anymore. So the coupling is mediated by the lattice or dielectric properties of the materials and connected to the electromagnetic properties of light. So this is kind of still, of course, the limit of the low wave vectors corresponding to the large wavelengths of tens of micrometers defined by light. So can we move even further towards just the short wavelengths through Magnons? So the answer is yes, and my colleague Dima Afanasyev will talk about this at 2 p.m. today. So I won't spend much time on this, but I want to maybe very briefly show our latest theoretical results done together with my PhD student, Ruben Lenders, who also presented it on the poster yesterday, where we calculated the generation and detection of the spin waves in antiferromagnets excited by the strongly localized femtosecond or terahertz pulse. So here the confinement is due to the absorption, for example, characterized by the penetration depth D, which can be as small as 50 nanometers, as will be discussed in 2 p.m. And we can solve equation for the spin deflection angle of antiferromagnetic vector in response to this effective magnetic field. And what we can see, so for different parameters, for either impulsive or displacive excitation, and for different boundary conditions of free or pinned spins, we essentially get the excitation of various spin wave packets, the property of which will depend on the character of the excitation and the boundary conditions. So here are corresponding snapshots. So there are, we can also calculate the spectra. And finally, we can even calculate the detection by the reflected femtosecond pulse. So here we have this big formula, but important part is actually here. So the formula had a pole, which corresponds to the Bragg condition when the wave vector of the spin waves matches the double projection of the optical wave vector on the spin wave. And changing the optical wavelengths, we can essentially pick up different points at the dispersion curve of the spin waves. And the experimental realization will be discussed later by my colleague, Dima. So with this, I would like to thank you for listening, and I hope that I convinced you that electromagnetic component of Magnons at Terahertz frequencies is not negligible, and it can also manifest itself in many conventional experiment geometries. Thank you for your attention.